So, once again, remember we're not having lecture on Thursday, nor will there be a problem session. But there will be a problem set. But because of this delay, that problem set will be due on Thursday, on the 26th. Okay, so we'll have some time to discuss it. We'll have a makeup lecture a week from tomorrow in the evening. Right, and the exam is coming. The exam will be 2 weeks from tomorrow. And that exam will cover through lecture 8, which was the lecture about the avoided crossings and perturbation theories. Okay, it won't cover what we're doing now, the fine structure and hyperfine structure and relativistic corrections to the hydrogen atom and other atoms. Okay, so we'll talk more about that next when we come back. All right. All right. So last time we were discussing an important application of perturbation theory. We were looking at corrections to the spectrum, that is, say, the stationary states of hydrogen, the energy levels, due to, in this first instance, relativistic effects to lowest order. So those relativistic effects are there because the electron is moving not too small compared to the speed of light. And, I mean, it's small, it's not that small. And so there will be corrections. And the lowest order corrections are of order alpha squared times the characteristic energy of the Hart tree. Okay? So we're looking in atomic units. The first corrections are of order alpha squared. Okay? Sometimes you'll see this, though, also written just, there is this relationship between the Hart tree and the rest mass of the electron, the rest mass energy of the electron. This is the mass of the electron. If you plug all those in. So the Hart tree energy is alpha squared smaller than the rest mass energy of the electron. And the relativistic corrections are sometimes seen as, if you look at them, not in atomic units, but in relativistic units, then the relativistic corrections are order alpha squared, alpha to the fourth, compared to the rest mass energy. Okay? Yeah.
Is that a coincidence, or is that?
No, yeah. It's there. I don't think there's anything deep about that.
Okay.
Yeah. It's numerology.
Okay.
Yeah. All right. So what one finds is that the corrections to the bare hydrogen atom, just the Coulomb interaction, that are of this order involve these three terms. There is one term which is the spin-orbit interaction. And the spin-orbit interaction we understood as a magnetic effect. That is to say, at the position of the electron, there is a magnetic field that is arising from looked at from the point of view of the electron, the proton is going around in an orbit around it and creates therefore the proton has a current, it creates a current loop that makes a magnetic field, and the interaction of that magnetic field with the spin of the electron, because the electron has an intrinsic magnetic moment, thus gives this spin-orbit coupling, L dot S. In addition, there are a couple of other corrections. One is the correction to the kinetic energy beyond, and when you think about relativistic kinetic energy. Okay, so there's this should be alpha p to the fourth, pardon me. This is all in dimensionless atomic units. And then there's this other term that is something that we could not see from classical theory. It arises due to the fact that the relativistic electron theory is really an approximation to the full relativistic field theory, which has both electrons and positrons. And the combination of those to lowest order gives this so-called Zitterberg gradient, which gives this smearing out of the electron position that gives this extra term, which is known as the Darwin term. Okay, and they're all of this order, alpha squared, in atomic units. Okay, and so we thus did perturbation theory, which is to say we want to look for the new eigenstates and eigen values to this order, to lowest order, in this case alpha squared, given this total perturbation. Okay? And so we do that, say, in a degenerate subspace, for example, the n equals 2 subspace. So we have to do, in general, degenerate perturbation theory. And we have to diagonalize this Hamiltonian, the relativistic Hamiltonian, in this subspace. Okay? And we could do that by inspection without actually writing down a matrix and diagonalizing it, because we can just look at this and see what its eigenvectors are. Okay? That's what we did. And we did that by noting that, well, what the way in which these Hamiltonians act, these guys only act on the radial degrees of freedom. That's to say, they have nothing to do with the orbital motion because they depend on the magnitude of r or p. Okay? So they don't mix. I mean, these are my zeroth orders. I'll write them this way. Eigenstates. There's a radial state, there's a spherical harmonic, and then we have the spin of the electron, up or down. Okay? These Hamiltonians, are all going to be only going to have matrix elements relative to this. They have no off-diagonal elements for different m's of L or different m's of S, right? This Hamiltonian, on the other hand, couples L and S. And what we did in that case is we noted that these guys are eigenstates of J squared, L squared, S squared, and JZ, where J is the total angular momentum of the electron, spin plus orbital. Okay? So L dot S is diagonalized in the coupled representation. It is not diagonalized in the uncoupled representation, okay? So what we say is that in the presence of spin-orbit coupling, the good quantum numbers are no longer L, M sub L, S, and M sub S, but J, L, S, and MJ, okay? And of course, this is the same, right? Because there's no mixing there. These are all with the same. We're not mixing different L in this case. Now, one thing just to remember physically here. Good quantum numbers are associated with conserved quantities. The good quantum numbers are associated with observables that commute with the Hamiltonian because they are simultaneously eigenstates of those observables and the Hamiltonian. So in the absence of, say, spin-orbit coupling, what we said, you know, when we just looked at this, we said the good quantum numbers are L and M sub L because we had spherical symmetry. And because we had spherical symmetry, angular momentum was conserved. And because angular momentum is conserved, the L is a good quantum number, and the projection along any axis is a good quantum number. Now, when we have spin-orbit coupling, we have to think a little bit more carefully because it's not only the orbital degrees of freedom that matter, but also the spin degrees of freedom. Okay. So what that tells us in this case is that, well, angular momentum is still conserved, right? Where would it go? The total angular momentum of the system is still conserved. But it's the total angular momentum that matters. Not just the orbital, or not just the spin, but the total angular momentum is now conserved. So it's now that J squared commutes with the Hamiltonian, not L squared or L squared independently. So whatever we put into the system, it must be the case, unless there is an external torque that is changing the angular momentum in some way, the total angular momentum of the system is conserved. Okay? So that's why J is a good quantum number. If there's no coupling between L and S, then they're independently conserved. And then these are perfectly good quantum numbers. Okay? So when we looked at, these are our new eigenstates, and then we just can look at the first order corrections by taking these eigenstates and looking at what the corrections to the eigenvalues are. Right? They're just the expectation values of the perturbation Hamiltonian in these new eigenstates. And those corrections look like this. And those corrections, what we see is that, well, of course, they can't depend on MJ because there is no direction in this case. MJ is the projection of the total angular momentum along some axis. And there's no difference between any direction. It's spherically symmetric in that sense. Okay? So we're always going to have, if we don't have any other external perturbation, we'll talk about such a perturbation maybe today, then it doesn't depend on MJ, but moreover, what we see is that it turns out it only depends on J and not on L or S. S is a half. This is just one electron, so it's never write it down because S is just a half. And we see that actually this is seen from the solution that you get from the Dirac equation, which is the equation for the relativistic electron-positron spinner. It only depends on J, and this is what we get. So the spectrum, or the energy levels, I should say, of hydrogen, say for the first excited state, n equals 2, well, so the effect of the spin-orbit interaction is to split states such that we typically will write this in spectroscopic notation. There is a principal quantum number, an L for the orbital, and a J. Okay, that's the notation. So states with different J are split. Okay? Those states, they all have the same radial wave function, but they have different superpositions of ms and ml, right? Through the Clebsch-Gordon coefficients to get a coupled representation of total J. The S state is not affected by spin-orbit interaction because it has no orbit. Its L is 0. So that state. So if I just had spin-orbit interaction, I would see this kind of splitting. But when you include both the spin-orbit and these other terms, the kinetic and Darwin term, what you find is that you recollapse these two guys together so that they become degenerate again. Okay? That's a special symmetry in hydrogen. And then what we said is, well, actually these guys aren't actually degenerate. There is a correction due to the fact that the electromagnetic field itself is also quantized. The vacuum fluctuations of the electromagnetic field act to cause a shift of the S state relative to the P state that's known as the Lamb shift. Okay? And this splitting is known as the fine structure splitting of hydrogen. And this splitting, just in terms of what the units are, I mean, this is like a microwave frequency, about 10 gigahertz. And this is about 1 gigahertz shift. Now, there's one thing I want to emphasize in addition about this. This kind of spectrum is similar, but not exactly the same for all of the atoms that have one valence electron in group 1 of the periodic table, the alkali atoms, right? So we have the group 1 of the periodic table. Right, we got hydrogen, lithium, sodium, rubidium, cesium, francium. Okay, all of these atoms have one electron in the valence shell, right? So their spectroscopically, or their energy levels, are similar to hydrogen, but not exactly the same in structure because of one thing that we looked at in one of your homework assignments, okay? So hydrogen is special because we have to 0th order, we have degeneracy in L. So to 0th order, what we saw here is that the 2s state and the 2p state were degenerate. That's only because we have the potential is 1 over r. But you solved in your homework when you have the kind of situation where, like in helium or lithium, where I have, you know, the nucleus, I have some closed shell of electrons, and then I have the 1 valence electron. That the potential it sees is not 1 over r, but something different inside, right? And what we solved in that homework assignment is that the lower L states the states which have the head-on collisions, which have much closer approach to the nucleus, are much, much more deeply bound than the higher L states. There's nothing near a degeneracy in L. So there's a huge splitting between the 0th order here has no degeneracy in it. Not at all, not even close. It's of the same order as the binding energy itself. Okay? So, for example, in lithium, right, so lithium, the lowest state here is the ground state. Well, you have the closed shell of the 1s, and then you have 1 electron and 2s, right? So we have a 2s here. And then we have 2p. But 2p is totally separated from 2s to 0th order, just due to the Coulomb interaction. Okay? Having nothing to do with relativistic anything. It's just the fact that there's a totally different kind of charge distribution when you have the closed shell. You know, and this separation here is, you know, yeah, I don't know, it's like yellow, 670 nanometers the wavelength. Now, then we put on relativistic corrections, okay? And so what's that going to do? Anybody have a thought about that? How are these energies? This is the 0th order. This is, say, lithium 3, or lithium 6. What's the relativistic corrections going to do here?
A little lower here? No.
Well, it sort of depends on how big spin orbit is relative to kinetic corrections. I mean, if we look back here, some of these went up and some of these went down, right? But the main thing that happens here is that these get split, right? So here, I didn't take into account the spin. Now I have spin. It's the same kind of thing. I have an L equals 1 added to spin a half. So I have J equals 3 halves or J equals 1 half. So this gets split in some way into a 2p 3 halves and a 2p 1 half. Okay? That's the, you know, and the combination of the relatives. This is the fine structure splitting. And then, you know, this guy, you know, it shifts in some way, but it's 2s 1 half. Okay? And this splitting can be, you know, a lot bigger. The things are moving faster. This splitting in lithium is 515 gigahertz. Okay? And then if you go to some much heavier atom like cesium, where the things are moving really fast because they're in these much bigger Z nuclei, then the fine structure splitting is huge. But it has the same basic structure. What you have in that case is now the valence shell is n equals 6, so I have this 6s 1 half, the 6p 1 half, the 6p 3 halves. Okay, this is sort of this is the ground state, and this is the splitting of the first excited state into, and this difference can be huge. I mean, it's nothing near like a tiny microwave frequency. For cesium, this has an 894 nanometers, and this is 852 nanometers. And this splitting is hundreds of terahertz, 351 terahertz. terahertz, I believe. I mean, it's very hard to, you can't even tune a laser. You have to have a very fancy laser to be able to go from this frequency to this one. They're completely separate. These guys, you know, have jargon names. This was first observed in the sodium spectrum, where they saw these two lines were split into a sodium doublet. And so they called the two lines D1 and D2, and we still do call them the D1 line and the D2 line.
But then to what degree the first order correction is a small perturbation?
It is, oh sure, it's still a small perturbation. I mean, this is 350 terahertz, but what is this? Okay, I mean, that is 1,000 terahertz, right? This is an optical frequency. This is, you know, a fraction. Okay, so it's a perturbation, but it gets to be not as small. It's still small compared to that. Yeah.
So are all these things pretty much, you know, I mean, are these perturbations, like, they don't have like any other perturbations that they see or any other structure that they see? Is this pretty much the whole story, or?
No.
Okay.
So we're going to talk about the next part of the story. What we have considered so far, we have the Coulomb energy, and then we had these relativistic corrections, which included effects like spin-orbit coupling. And that spin-orbit coupling arose because the electron has a intrinsic magnetic moment, and that intrinsic magnetic moment interacted with the magnetic field presented to it in its rest frame. Okay? What we haven't thought about is, what about the nucleus? All right. So we just said there is this proton and it's there and it takes, but the proton has a spin. Okay, we typically call the spin of the nucleus I. It's a spin angular momentum. The spin of the nucleus for a proton is a half. For cesium, the one that's not radioactive, 7 halves. Because of course it has neutrons, and the protons and neutrons combine in some funky way to make some big spin. Right? But this is, there are quarks inside there over there. All right, so there is a proton magnetic dipole moment, which is proportional to its spin angular momentum. Okay? And well, what that turns out to be, it's complicated, because I said it really comes from the underlying elementary quarks. It's one of the things we don't understand exactly. So, Professor Fields here, that's what his research is about, how you understand where the spin of the proton comes from some nuclear strong, it's a hard problem, the strong force and all that stuff. But phenomenologically, just measuring it, what we find is that, well, if it were just a spinning ball of charge E with the mass of the proton, then it would be the nuclear magneton in units where this is in units of h bar. Okay, where the nuclear magneton is h bar over twice the mass of the proton c. So this would be if you had a angular momentum h bar over 2 spinning with that angular momentum with that mass, that's what you would expect. But that's not what you find. There's a g factor, the g factor of the proton. And that's just phenomenological. It's not something that we know how to derive. At least I don't know how to derive it. It's about 5.6. Okay? So that, again, is coming from some underlying nuclear physics of quarks and gluons underneath that makes up the proton. Okay, so what does this mean? How does this, well, first of all, how big are forces or energies that are arising from the fact that there is this magnetic dipole moment coming from the proton? Well, I mean, when we had for the electron, right? The electron magnetic dipole moment, the interactions that arose from this, well, they gave rise to things like the fine structure. So these things are going to be on the same order, but reduced because this guy, of course, the g of the electron is minus the g factor of the electron, the Bohr magneton, the spin of the electron units of h bar. This is the electron, the magnetic dipole moment. And the Bohr magneton depends on the mass of the electron. Okay? So this is way bigger than this, just because of this mass ratio. Okay? So the nuclear magneton, which we said was about called n, divided by the Bohr magneton is this ratio, and that's a half of a MeV divided by a GeV, right? So this is very small. So the effects that arise from the proton spin, they're also relativistic, but they're down by this factor, squared. So they don't give rise to fine structure. They give rise to hyperfine structure. It's hyperfine. Okay? So this effects that have to do with the proton, like the proton magnetic dipole moment, or in bigger Z atoms where the nucleus is not really a spherical charge but has some quadrupole moment. All of that gives rise to hyperfine split. And that's what we're going to talk about today.
So the hyperfine is somewhere in between the first relativistic correction to the second relativistic correction, or should it be taken on the same order as the second relativistic correction?
It's on the same, it's of order alpha squared times this factor squared, right? So it is smaller by a factor of this squared compared to the lowest order fine structure.
But still, we don't need to go to the second order of the relativistic effect. Okay.
We'll see what mixes what.
Yeah.
All right, so now we have to ask ourselves, what is the perturbation Hamiltonian that is arising from this thing? Okay, so we can think about this in the following way. here's my proton nucleus. It has some intrinsic magnetic moment. And there's some magnetic dipole field coming from it. Okay? And so this is the B that's coming from the proton, due to the fact that it has an intrinsic magnetic dipole moment. Any magnetic dipole moment has associated with it a magnetic field. Okay? What is that magnetic field? Well, we have to dig back into this. Yeah, come on, see, 4 or 5. So there's lots of ways we can think about it. One thing to say is that, well, there is a vector potential associated with a magnetic dipole moment.
We know this one.
Oh, you do?
I always get the order of the cross products, but you
All right.
cross it.
Yeah, there's some stuff like that. Let's see, this is right. Okay, so this is the dipole moment of the proton crossed into where E sub r is, so we have some vector. Along the radial direction, right? So that's the vector potential. Okay? And now we have, so what is the interaction Hamiltonian with the electron? Due to the spin of the proton. Well, we have 1 over 2m, the momentum of the electron, minus E over c, the A due to the proton squared, minus the mu of the electron due to its spin, dotted into the B of the proton. Those are the effects that we saw in the Pauli interaction. There's the part that has to do with the motion and the part that has to do with the spin. Okay?
I've got a quick question.
Yes, please.
I thought when we did that for the electron and the spin orbital coupling, if I remember right, I don't remember the
Yeah,
coupling to the A field.
I didn't do it that way because I did it more intuitively. But we could have.
Okay, okay.
And in fact, so this term, when we plug this in and do the squares and do some manipulations, we find that this is equal to the following. This is equal to, how do I want to write this? This is equal to 2 mu b L dotted into the proton divided by r cubed. Okay, that comes from things like r cross p when you're, I'm going to want to go through all that algebra. Now, how do we understand what this term is? Because I could have done this more intuitively. Well, remember what we have here is we got this electron orbit. And here's my electron, it's got its own spin. But it's orbited, generally, with some orbital angular momentum, right? Now that orbital angular momentum of the electron creates a magnetic field because it's a current loop. And that current loop creates a magnetic field at the position of the proton. What is the magnetic field associated with a current loop? Well, it's if it has a loop. This is the magnetic field. This is the magnetic field of the orbiting electron at, or minus it. No, it is not. Yeah, this is minus it. Because the electron charge is minus. At the proton. So this is what that is. This is, again, a minus mu proton dotted into the B of the electron. That's what this term is. That's kind of what I feel in that when I looked at the fine church. The mu of the electron, of course, is minus 2 the Bohr magneton times the spin mu of the Bohr. Right? This is the G factor. It's a negative charge. What is the B? Well, the magnetic field coming from the proton at the position of the electron is equal to the curl of the vector potential. Yeah. All right, so we do that and we get the following. We plug in for that A. We get 3 mu B minus mu P dotted into E sub R over R cubed. But then we have this singularity term. That's what you get when you take the curl. How do we understand this? Well, this is a problem. This is a kind of familiar dipole field coming from a magnetic dipole moment. So this is a dipole field. What about this term? What the heck is going on here? Well, I can think about, if I go back here, that if this proton were really a magnetized ball of a certain size, there would be a magnetic field inside here, right? I mean, it looks like that. You remember those problems from Griffiths? Maybe. So, but this is like a point particle, so as we shrink this, there's a delta function right here. So this is the limit of this magnetized sphere shrunk to a point. This is called the contact term. This is only at the position of the proton, the orange. All right, so that's what we're calling H8 hyperfine. That's our perturbation. So let's write it out. So I'm going to write this, take out all the units here. My hyperfine Hamiltonian is equal to 2, the G factor of the proton, the Bohr magneton, the nuclear magneton, okay, because I always have this combination of mu P and mu B. Then I have that first term, which is coming from the interaction of the orbit with the spin of the electron. So that's L in units of h bar, I in units of h bar, I'll call that little I, over R cubed. So that's that first term. And then I have this other term, which is 3 I dot S minus I dot the unit vector along the radial direction, S dotted into the radial unit vector over R cubed plus 8 pi over 3 I dot S delta function at the origin. All right. Now, if I want, I can make all of this dimensionless and bring out that, the Bohr radius cubed. And then I can make this in I could make this relative to the characteristic energy over here, right? And when I do all that, put all that in, all this goes away. Let me not do that yet because I don't want to confuse too much. I'll see what, I'll come back to that in a moment. Let's leave this for now. All right? But this is going to be of order alpha to the 4th times alpha to the 4th times the ratio of the electron mass to the nuclear mass. All right. So that's our perturbation Hamiltonian, right? So what the heck are we doing? We are going to now have to diagonalize the Hamiltonian with respect to this. Now, what we have, our Hamiltonian here is H0. This is just p squared over 2m minus p squared over r, right? We have the fine structure Hamiltonian, that's what we wrote down over here. And then we have the hyperfine Hamiltonian. Okay, those are these things. Now the way we see is that this is a small correction relative to this. So what we can do first is think about this as my new H0, and this is my perturbation relative to this. We've already found the eigenstates of this, and now we're perturbing the fine structure with the hyperfine structure. Okay? So, in the new H0, our good quantum numbers were N, L, J, S, and Mj. Okay? Of course, there was the nucleus there, but we just didn't care about it because it was every state in that in here in our fine structure was in fact doubly degenerate, corresponding to proton spin up and proton spin down. But we just didn't include that degeneracy because the nuclear spin didn't couple to anything, we wouldn't even see it. Okay. And then we have the hyperfine interaction, which looks like this. Okay. And now I is no longer separable from the total angular momentum of the electron, from J. There is a coupling of I to L and a coupling of I to S. So, what do we do? Well, once again, what we have to do is look for the new eigenstates of the system with respect to this. It's a complicated mess. So we're not going to deal with this, at least right now, in its full glory. Let's look at this for the specific case of the S states, just to start. Okay, so let's look at the ground state of hydrogen and ask how the ground state of hydrogen is perturbed by the hyperfine. So let's start. All right, the ground state of hydrogen, n equals 1. L equals 0, the 1s state. How degenerative is this?
It's not degenerate.
It is degenerate. There are many different states that have exactly this energy. What are they? I think there are 4 actually.
Could you have like spin up protons, spin down electrons, and
Exactly. There are the 2, there's electron up and down, and nuclear spin up and down, right? I mean, so in this case, because J is 0, I mean J is a half, right? Because L is 0, S is a half, and J is, there's only one possible value of J. The Mj values are actually the Ms values in this case. So the 1s 1 half, we have, in this case, we have 4 states. We have up electron, up proton, up electron, down proton, down electron, up proton, down electron, down proton. Right? These are shorthands for S, M sub S, tensor I, M sub I. Right? And then, of course, there is the R1s state. That's the radial guy. And the YLM is what is 0, 0. Yeah.
so the J still only applies to the total angular momentum of the electron.
That's correct.
It's not the entire system.
That's correct.
Okay.
That's correct. However, now the total angular momentum has nuclear spin, right? So we define J as electron and proton spin. Okay. That's what F means. What do we expect to be the good quantum numbers once we include the Hyperfine interaction?
L squared, J squared, S squared, I squared.
So, wait, keep coming.
Oh, what the ones on 70? So,
Well, let's just first think about one thing I said at the beginning of class. The total angular momentum of the system is conserved. So what are at least good quantum numbers there?
F squared, FC.
Right. So F squared and Fz will be, and then also we got J squared, we got L squared, we got I squared, we got S squared, and that's it.
The name doesn't.
Yeah, and then, of course there's.
Okay.
And then. Sometimes why. All right. So, of course, this for hydrogen, I mean, these guys are fixed. So we would never write these. This is always, you know, the I is a half. So there's no We don't need to write down. It's a spin, it's a proton spin. It's never going to be anything different. And it's one electron, so the spin is a half. We'd never write that down. Of course, if we have multi-electron atoms with more than one electron in the valence shell, then we got to worry about that. And a mess, excuse me. All right. So, what we had then is that without hyperfine structure, we had states that look like this. We had N, L, J, right? I'm not going to write the S, right? And then there was tensor I, M sub I. All right. Now what happens? Well, the hyperfine structure is going to mix these guys together. It's not going to mix states with different J, because they're split by the fine structure. So the lowest order, so let's look at an example. Let me look at, for example, here's, just to write it down, I got my 1s, right? So this had these 4 states, right? The 4 states correspond, in this case, J is a half, M is a half, or minus a half, I is a half, M sub I, right? So we have up, down, down, up, and up, right, for the electron and nuclear state. If I had the 2s, I mean the n equals 2, we have, you know, this kind of stuff that's going on, right? And this is the 2p, 3 halves, the 2s, 1 half, and the 2p 1 half, right? Now I ask you, what is the degeneracy of each of these levels? What's the degeneracy of this level? Two for M sub j, and then 2 for the spin of the nucleus. This is 4-fold degenerate. This guy has 2p a half, with spin up and spin down. Mj is a half, and it also has 2p a half with mj equals minus a half and spin up and spin down for the nucleus, right? Remember, there are 2j plus 1 different sublevels of just do the electron angular momentum, and then I have 2 of these guys, right? What about this guy? What's its degeneracy?
We're still ignoring hyperfine, right?
Right, right now I'm just saying without the hyperfine.
Okay.
What's the degeneracy of the 2s state, including the nuclear spin? It's also 4. It's exactly the same, right? You got mj plus a half, mj equals minus half, and spin up and spin down. What's the degeneracy of this guy? It would be 8, because there are 4 m sub j's times 2, right? Okay, and then we put on the hyperfine. Now what's going to happen is the hyperfine energy is small compared to any of the other energies. So it is degenerate perturbation theory within a 4-dimensional manifold, a 4-dimensional manifold, an 8-dimensional manifold, and a 4-dimensional manifold. And we mix the mj and mi's to get m sub f's. All right? And the total f quantum number. So these guys will split up. We'll come back to the n equals 2. Let's start with this guy. It's easier to deal with. All right, so hyperfine perturbation on hydrogen ground state. And equals 1, L equals 0. That's a half. I is a half. Firstly, if I look at the hyperfine Hamiltonian, what we see is that this guy is 0. Why is that?
Because L0.
Because L 0. There's no orbit, so that term doesn't contribute. Now we have to look at these other terms. Okay? So now I have to consider, right, so this is the 1s radial wave function. The y00 in the absence, and now we're going to mix these guys together. Now, if I look, one thing to note, let's look at matrix elements. Consider matrix elements. I dot S minus I dot E sub R S dot E sub R over R cubed.
Okay. In general, the MS shouldn't it be J and J? Because J is
It should, yes. It should generally be
But-
that. But
yeah,
in this
it's
case,
zero.
L equals 0,
Yeah.
they're the same thing. But you're right. Generally, it would be J and J. I mean, generally, we would not have this separable.
Sure.
This is L equals 0 and L equals 0. This would generally be J and J
Yeah.
for something that's not an S state. Now, this is a little bit of a tricky business here. Notice there are two kinds of degrees of freedom here. Things that have to do with the position of the electron relative to the proton, the orbital degrees of freedom, and spin degrees of freedom, both of the electron and the proton. Okay? So we take this guy, this product state, and we do this matrix element. They all have the same YLM, the same radial integral, but they can have different spin up and spin down. Those are the 4 different combinations. Now, here's the trick. If I look at this guy, because it is integrated over a y00, which is spherically symmetric, this is a dipole field, right? And if I integrate a dipole field over something spherically symmetric, it's 0, right? This is 0 because this is a dipole field, and I'm integrating it with respect to a y00. So for the L states, for the S states, for L equals 0, this is 0. Yes, Steve, you had a question.
I was going to suggest that in non-dipole cases, you can automatically get rid of any states where the MS's and I's, prime and non-prime, are not the same, because if they're opposites, wouldn't they technically equal zero?
No, they won't generally, because you know, you have to write this out. If I write out, let's look at it's a good question. Let's look at an MSMI I dot S type term with an MS prime and an MI prime. How do I do that matrix element? Well, I'd have to write this out as IX as X plus IY SY plus IZ SZ, right? And those are each Pauli operators for spin 1/2. One that acts on the spin of the electron space, one that acts on the spin of the proton space. And these terms, of course, you're correct, don't connect MS and mine, but these terms do. Okay? Which is to say that for I dot S, the I dot S interaction is not diagonal in the product basis. It's diagonal in the couple basis, which are superpositions of spin up and spin down of the proton. So this term is zero also for the L equals 0 states, the S states. So we're left with the contact interaction. So the contact term. So that tells me that I need to diagonalize this Hamiltonian in the 4-dimensional subspace where MI and MS are each plus or minus 1/2. How am I going to do that? We use the same trick we did before. I dot S, well, let's consider F is I plus J, right? That's what we said is the total angular momentum. F squared is I squared plus J squared plus 2I dot J. So that means that I dot J is 1/2 F squared minus I squared minus J squared. For S states, it's the same thing as I dot S. Where L is 0. I dot S is 1/2 L is 0. So, what this tells me is that this Hamiltonian is diagonalized not in this basis, the eigenvectors, the new eigenvectors of the system are 1s tensored into f, m sub f, where I and s are also good quantum numbers, but we just, so we go from the uncoupled of proton angular momentum and electron angular momentum to the coupled representation of total angular momentum f and m sub f. That's what we had here, are good quantum numbers. Right? Yeah.
So do I and j commute then?
Always. I squared. I mean, remember they live on any operators. If I have a tensor product space, if my Hilbert space is a tensor product of two Hilbert spaces, any operator on this space commutes with any operator on that space.
Okay, but they're, okay, because we're ignoring, well, I mean, it looks like they're coupled or something. I guess
They are coupled.
But
yeah.
I guess I'm not, okay, I must not.
They're coupled, which says that the good quantum number is not the product state of I and S,
Okay,
but the total angular momentum states.
okay, so that doesn't mean, okay, I thought that those, okay.
It doesn't affect the question I think you're asking is, how was I able to write this as 2I dot S and not I dot J plus J dot I? Well, I and J commute.
Oh,
Doesn't mean that they're not coupled.
Okay, that's what I thought,
Right.
those were the same thing.
They're not the same thing.
Okay, thank you.
So now we just have to find what the splitting is. All right, so my rewriting this hyperfine interaction, the contact term for the hyperfine interaction is 8 pi over 3 times a half f squared in units of h bar, if I like. I left out all of the prefactors. There's a lot of prefactors here.
Are they in the notes?
2g, yeah, they're all in the notes. 2g proton over a cubed. Okay, there are prefactors here. Minus I squared minus s squared times the delta function at the origin. Okay. I squared, so we look at the expectation value of these guys, so my energy, my E1 hyperfine for the given f m sub f is equal to 1s f m sub f, the new eigenstates. Okay. Of course, I and s are good quantum numbers. What is the eigenvalue of I squared?
I times I plus 1.
I times I plus 1. And I is a half, so that's 3/4. And this is s times s plus 1. So that's also 3/4. So this is f squared minus a half. No, that's not right. 3/4 and 3/4 is 3 halves. Okay. For I is a half and for s is a half. Okay? Times the identity. So, putting it all together, I find the following. Oh, great. This energy is equal to some constant, which I called A, times over 2. The eigenvalue of F is F times F plus 1 minus. Where A, this little value of A, in units of Planck's constant, is 1.42 gigahertz. So, what does the ground state do? Let's go back to this board. We had this fourfold degenerate subspace in the absence of hyperfine structure.
Does it split it?
It splits it. It splits it depending on the value of F. What are the possible values of F?
1, 0,
No.
For
F,
mass?
remember, is the magnitude. It can never be negative, okay? So let's be careful about that. F is the magnitude. So F is the total angular momentum. We're adding together the electron angular momentum and the nuclear angular momentum.
One.
What are the possible values?
There's 1 and 0.
1 and 0. So I can have, when F is 1, I get 2 minus, so that's 4 halves, that's, goes up by
So it splits it into 2 levels of 2.
in 2, they're 2 levels, but they're degenerate. This goes up by A over 4 for F equals 1, and it goes down when F is 0 by minus 3/4. So that this splitting is A, and this is F equals 0.
That'd be 3/4, I think.
Should be 3/4.
So the 2 levels of twofold degeneracy.
Well, let's think about that. Let's come back and complete the thought here. So this is the ground electronic state of hydrogen. 1s. We have the F equals 1. What is the degeneracy of F equals 1? 2F plus 1, which is
2, 3.
3. So I end up with, so this is F equals 1, and there's M sub F is minus 1, 0, and plus 1.
Just like the elephant.
And then we go down, and we have F equals 0. And F equals 0, what is how much? It has only one state. It has MF equals 0. And this splitting is 1.4 gigahertz, and or lambda is 21 centimeters. This is the famous 21 centimeter line that people make their whole careers off of. It's radio astronomy is all based on this. That is to say, the flipping, if you have a collision of 2 hydrogen atoms in a gas, and you flip from this state to this state, you will emit this, it's really a microwave, but we call it radio photon, which has a wavelength of 21 centimeters. Finally, what are these states when written in terms of spin up and spin down of the proton? Those are our 4 states. So what is this state written in terms of spin up and spin down of the electron and proton?
Has to be the both of these spin up.
They're both spin up. So this is up electron, up proton. That's a stretch state. And this one is down electron, down proton. What about these guys?
Up up electron, down proton is F equals 0.
But it's not a product state, right? This is the symmetric combination up, down, plus, down, up. And this is the anti-symmetric combination. Up, down, minus, down, up. You remember triplets and singlets?
Yes.
We'll talk a lot more about them soon. This is like the singlet combination, and this is the triplet combination. Total spin 1. These states are not product states of electron and nuclear spin. They are entangled states, if you like, of electron and nuclear spin. They have total spin projection 0. They don't have but their individual spin projection is not well defined. The total entanglement is. All right, we better get out of here because we're going to run into the next class. I'll take questions now.